In this video, we're going to look at what the gain bandwidth rating is for an op amp. I think we know what gain is, and so let's work on defining bandwidth. And then the gain bandwidth rating is actually just the product of the two. So op amps do fine with frequencies all the way down to 0 hertz. They can handle DC, if you remember. And so the output will have no trouble with low frequencies, and on our plot here we can just represent the output doing fine. And then as frequency increases, there comes a point where the output does start to fall off. And as you go higher, the output falls off more and more and more, and so on. So this is the frequency capability of an op amp. As frequency increases, we do start to run into trouble. The op amp starts to struggle with the output, maintaining it, and so it does decrease and start to fall away. When the output falls to 0.707 of what it was, so it was up here doing fine, it's falling, falling, falling. Here's where we call it a day, right here. It's down by 70.7% of what it was when it was doing fine, which is here. It's all along here. And now the attenuation is starting. We get to a point where the output falls to 0.707 of what it was, and we're calling it a day there. Call that the cutoff frequency. So this is the bandwidth right in here. And for op amps, the bandwidth is always this upper cutoff frequency because the lower frequency is 0. It can go all the way down to 0 hertz. So it's true for op amps that this cutoff frequency is the bandwidth. Bandwidth is always the width of the frequency range where the signal stays above 0.707 of what it is in what they would call the pass band up here. And we can just put an example frequency here to make this sort of come to life. Let's say my op amp has no trouble. I shouldn't say no trouble, so let me get back to that. But it can go all the way up to 1 megahertz, at which point the output has fallen down to 0.707. So I want to back up. When I said it has no trouble, it starts running into trouble here, which is a very good thing to always remember about bandwidth ratings. At the bandwidth rating, we're down 0.707. So then you have to back up and say, whatever the bandwidth rating is for the op amp, or I want to broaden that to oscilloscopes or anything that has a bandwidth rating, you always have to remind yourself that the bandwidth rating doesn't necessarily point to the usable range of frequency. It points to the cutoff point that is universal, and that is 0.707 down. So when you think about bandwidth rating, always remind yourself that if you're looking for the usable range where the output essentially doesn't suffer at all, you might be backing up way up to here for some kind of an idea of what the usable range is for a given device or op amp or system. So that's something always to keep in mind. You have to pick a point, and there's reasons to pick 0.707 that we'll talk about next. as far as making some universal definition for bandwidth, but that is the universal definition. So when you, for example, if you want to purchase an oscilloscope and it has a bandwidth of, you know, we can use 1 megahertz, um, understand that if you try to measure a signal that's 1 megahertz with a scope that has a bandwidth of 1 megahertz, you're not going to be able to measure amplitude accurately. That 1 megahertz bandwidth rated scope can measure amplitude accurately up to here, at which point you're going to get false information if you think that it's giving you the true amplitude of the signal, because it's going to start to attenuate the signal. It can measure frequency, no problem. The frequency will be accurate, but your amplitude of your signal is going to start to tail off earlier than the bandwidth rating. So always know that. So keep that in mind when you're speccing out systems or things that have a bandwidth rating. I always have to remind myself of that. That doesn't mean you're good to go. You're good to go for frequency measurements up to 1 megahertz with a 1 megahertz bandwidth scope. And if you don't care about the specifics of the amplitude, that's fine. However, if you're trying to get an accurate amplitude measurement, you're gonna only have a usable range somewhere in this vicinity. So why do we pick this 0.707? Well, like I said, we have to pick some point. I mean, where do you want to call it? And so that's the first thing. But then it has other meanings, the 0.707. So we'll look at those, and it also has other reasons. When we get to filters, you'll see why that's a good point to pick. Whether it's high pass or low pass, depending on your components, we'll look at the voltage division that occurs, and there's sort of a symmetry there to this 0.707. So there's lots of reasons. Let me look at the other definitions. 0.707. When your voltage drops to 70.7% of what it was, that is also going to be the half power point. So that kind of eliminates one reason. You're at half the power here. If you remember, power is V squared over R. So if it drops to that, then square that, and you'll see when you square 0.707, you're at 0.5. So it's half power. I can put 0.5 here. You're at half the power. And if you know decibels, which I can do a tutorial on that, we haven't done those yet, but it's also where you're down by 3 decibels. So those are things you'll see that will help it look a little more familiar. Cutoff frequencies, when we get to filters, they're always at the -3 decibel point, is where you say that they have your cutoff or your side frequencies and so on. We'll do decibels at some point. I'll straighten that out for you if you don't already know. Of course, at the bench, you can measure the bandwidth of an op amp. It's just a matter of finding this frequency where the output drops to 0.707 of whatever it was. And you can pick the whatever as far as the output. It is important to keep your output voltage small enough so that you don't accidentally run into slew rate distortion while you're checking for bandwidth. Think about it. If I have this output set for too high of a voltage peak, there's a chance as I run frequency up to watch for attenuation due to bandwidth. As I run the frequency up, it's possible if I have too high of a peak output that I'm going to hit slew rate distortion first, and that's going to mess up my search for bandwidth. So keep it small. I think with our 358, I don't know, maybe we'll pick like half a volt for V peak, just to keep the output low enough that it doesn't run into challenges based on its slew rate. Probably another good idea when you're doing a bandwidth measurement, you probably want to use peak to peak measurement in case there is any offset in the signal. That would maybe throw things off. So, we could pick, if we keep the peak voltage low to a half a volt, maybe, well, that's nice. It keeps our numbers real easy, doesn't it? We could do 1 volt peak to peak as our output, and when the output's doing fine for the op amp. And then all we're going to watch for, we're going to take the signal generator, the waveform generator in the analog discovery. We can start at 0 or very low frequency, however low it goes, and then just bring the frequency up and watch for the amplitude of the output of the op amp to drop to 0.707 of what it was. Well, if it was 1 volt peak to peak, obviously that's easy, right? We're watching for the point here where the output drops down to 0.707 volts peak to peak. And it's very important to add at this point, I think, that your scope screen is not going to look like this. I get that a lot sometimes. We'll dismiss the lab, and the students will have this in their heads as a way to check the bandwidth for their op amp. And they'll call me over, Mr. Evans, I can't get my scope screen to show this, and it won't. This would be known as a Bode plot. The analog discovery can do Bode plots, but in the YT oscilloscope mode that we're going to use at first, if you want to experiment with Bode plots later, we can. But just the standard YT mode, you're not going to get a plot of output voltage versus frequency. So what will you see on your screen? You're going to still be able to do this. Remember what you're trying to do. You have the op amp. Maybe you'll set it up as a voltage follower is a good plan if you're looking for bandwidth. Keep things simple. We've kept it very simple with our numbers, 1 volt peak to peak. So how's that going to look on your scope screen? Let's draw it. You're going to have a sine wave. Remember, we're checking with a sine wave. So the sine wave is going to be this 1 volt peak to peak, right? Sine wave on your scope screen. So you'll have your op amp set up as a voltage follower, and simply put 1 volt peak to peak in. You'll get 1 volt peak to peak out, as long as you have a low enough frequency to start low, and things should be fine. And on your scope screen, you're not going to see the Bode plot. You're going to just see the 1 volt peak to peak sine wave that you have. What I like to do next is simply put scope cursors right on the screen that frame in the 0.707 down point that I'm looking for. So if I had, these numbers are easy, if I had 1 volt peak to peak, 0.707 of that is 0.707 volts peak to peak. And but this is the time where you want to take your time to look at whatever this voltage is. If this was some odd voltage, like, I don't know, 2.36 volts peak to peak, take 0.707 of that, set up your cursors to mark the 0.707 value of whatever your peak to peak was. This then frames in the amplitude, the peak to peak amplitude that you're looking for. And if you don't have offset, you can use peak measurements. It's fine. If you have a preference, but you just be watching out for things like offset that can throw you off. I should mention in your analog discovery, if you have a lot of offset present, might be worth looking at the calibration routine. I think I remember seeing one. Might look that up and do a calibration run on your analog discovery. Sometimes the offset can come from the op amp itself, in which case the calibration isn't the answer to the problem. You just have offset, and so you have to watch for that. So with this setup, you're all ready to go. you've got your 1 volt peak to peak up on your scope screen. Again, nothing like the Bode plot looking like that. Now all you have remaining to do is crank up the frequency of your signal, of your input signal, and watch what happens. So you'll start to increase the frequency, you know, and oops, let's see here. It's gonna maintain the 1 volt peak to peak. You know, it's gonna get pretty busy here, right? So you might have to also change the volts, the seconds per division, the horizontal sweep rate. You might have to sweep faster to keep stretching it out. I mean, it's going to get more and more congested here. So sweep faster if you want to keep seeing your sine wave, and your sweep rate on your scope, your seconds per division. You're going to have to keep making that faster and faster. But what you're watching for is this peak to peak value to shrink down to the level that's marked by your cursors. The frequency that causes that is your cutoff frequency. It's the upper frequency limit to your op amp. Minus 0 hertz because it has the 0 hertz capability. So it is your bandwidth. You know, your upper frequency that causes this subtracted from the lower frequency, which is 0, is the same number. So so you're just looking for that's going to be your number that you say is the bandwidth of this op amp. So you're going to keep going, maybe stretch it out, but eventually you're going to get a sine wave that's in here, right? So when you get that one, and I mean this is a mess now, right? But I mean you're not going to see all of these. These will all go away, right? And this is the final picture that you're left with. So that's the progression. I think you get the idea, right? Um, but I wanted to really kind of try to do that physically for you because I always get asked or called over to a bench because students are asking me, well, I can't get this to show up on my screen, like I said before. But you're not going to. You're going to get a low frequency sine wave, and then you're going to keep going until you get to a higher frequency sine wave whose peak to peak value drops right within your framed levels of your cursors. When you do that, don't forget then you've got to look at what frequency caused that. So what is this frequency that caused the amplitude to reduce to 0.707 of what it was? That's your bandwidth for an op amp. And later when we do filters, of course, there might be 2 cutoff frequencies, an upper and a lower, but since our lower one's 0 hertz, like we keep saying, it simplifies to simply this upper cutoff frequency is synonymous with the bandwidth. So for our example, we could keep the 1 megahertz, just an easy number, and we could say that when we got to 1 megahertz, our amplitude dropped to 0.707 of what it was. So our bandwidth for this op amp is 1 megahertz. And now we can tie the two together because the rating that'll be on a data sheet for an op amp is called gain bandwidth. And we'll have to look at what do they mean by that. Well, gain bandwidth is simply a product of the two. It's you multiply them together. Whatever gain times whatever bandwidth it's capable of. They're trade-offs of each other. In other words, as you want to make a circuit with your op amp, if you want more gain, you're going to have to give up some bandwidth. It can't give you everything you want always. So I mean, if an op amp has a high gain bandwidth rating, it means maybe you can have high gain and high bandwidth, but it's still going to have a limit to what you can have in both camps. So they are always going to be a trade-off. I'll do a little chart here. Maybe that'll help us. If I wanted to build a circuit with a gain of 10, that would be my gain, and then there would be a certain bandwidth that I can achieve with the circuit of a gain of 10. If I wanted a gain of 100, my bandwidth, I'll have to give up bandwidth to get to the gain of 100. My bandwidth will be 1/10 of what it was. So let me put a little chart together and we'll be able to stare at that. Okay, so here we have a little chart and with super simple numbers. We ran our test circuit with a gain of 1, and we could get all the way up to a bandwidth of 1 megahertz. That means that the gain bandwidth product, right, that's what I wrote down here, this gain is 1 megahertz. I hope these numbers aren't too simple that they just start overlapping on each other too much. But the manufacturer of this op amp could maybe then specify the gain bandwidth product for this op amp is 1 megahertz. And what that means is you can pick whatever gain you want, but you'd have a corresponding bandwidth capability that goes along with that gain, or vice versa. If you need a certain amount of bandwidth, then you'll be limited to a certain amount of gain. And the chart, I hope, kind of shows you that. So if I only need a gain of 1, I can go all the way up to 1 megahertz, and I'll still satisfy, I'll still be okay, you know, maybe. Well, and okay, what do I mean by okay? I mean, again, we have to go back to this whole thing here, right? That gain bandwidth product specifies that if you have a gain of 1, you can go to 1 megahertz and have a drop of 0.707 at 1 megahertz. So that might not be okay. So I might be looking way back here to say that's my actual usable range. So there's lots of things to sort of keep in mind with all of this. We're not going to get all the way into splitting hairs or as far as backing up to find a usable range necessarily. I mean, we could, and if you wanted to do that with your analog discovery, you would have your 1 volt peak to peak and just watch for when it starts to drop even a little bit, and you can decide when you want to call it a day as far as usable frequency range. But the definition, though, is what we want to stick with for now, and that is what the rating from the manufacturer is going to be. It's going to be this gain bandwidth product rating. If this number's high, again, it's a good thing. You'll pay more for that op amp if it has a really high gain bandwidth product number. So for ours, again, it looks like we tested it out, and it seems like it has a 1 megahertz. And again, back to our chart, which I got away from here. We ran it with a circuit gain of 1. We got to a megahertz before it dropped below 0.707. Now, if we wanted to crank the gain up, and we will do that, we can try that in the lab, you would simply put some gain into the circuit here. So you could put you could go ahead and put a feedback resistor here and an input resistor. You can get a gain of 10. We know how to do that. So maybe with negative feedback, get an inverting amp or whichever amp, but get a gain of 10. And when you have your circuit set up for 10, the gain bandwidth product tells us that you'll only be able to go as high as 100 kilohertz before you hit this down by 0.707 point. So 100 kilohertz. If you need even higher gain, like a gain of 100, your bandwidth is only going to be 10 kilohertz for an op amp with a gain bandwidth product of 1 megahertz. Now this is very simple. The gain bandwidth product rating, for some op amps, as I've seen it, and I think I'm right about this, it's more of a constant than for maybe some others, and I say that with a little hesitation, but we can experiment again and sort of explore that. What I'm kind of hedging on here is the gain bandwidth product perfectly constant throughout the operating range that you might experiment with? Like, for example, throughout a gain of 1, 10, and 100, does the gain bandwidth product stay perfectly constant? And I want to say that I've seen that happen for some and not for others. As far as op amps, I kind of remember reading again somewhere, and we can experiment, see how our 358 stacks up, that the gain bandwidth product was not perfectly constant. It actually varied over an operating setup range of as you varied gain, but it still gave a ballpark range. So yeah, I'm hedging a lot there, and I know, and that's fine. And we can experiment to see what our 358 does. Does the gain bandwidth product stay constant? Looking in the one data sheet that I looked up, I didn't find a gain bandwidth product rating in the data sheet. Makes me think maybe the 358 doesn't hold a real consistent uh, number uh, when you multiply gain and bandwidth throughout a range. But if you see in the data sheet for an op amp that it has a gain with bandwidth product rating, they're trying to tell you this kind of a setup, and it should be more or less a constant for whatever setup you have. So you would see something like this unfold. You could try different gains, and we'll try that with our 358. We'll maybe try some different gains. Maybe we'll sit somewhere in 25, a gain of 25 and a gain of 50 or something like that. But that's the idea. Um, uh, maybe when you're looking to measure bandwidth, a gain of 1 is probably a good idea, and it gives you the bandwidth at a gain of 1, which also gives you the idea of what the gain bandwidth product will be. But yeah, we can experiment with different gains, and you should see. One thing I do know, whether it's going to stay perfectly constant, the gain bandwidth product, or not, you will see the trade-off. As gain goes up, bandwidth goes down. So if nothing else, we know we can hang our hat on that. That trend will absolutely present itself because, like we said before, they are trade-offs of each other. So we can at least stand firm on that. And how constant is the gain bandwidth product over the entire operating range of different gains? Not totally sure what we'll find with the 358. But again, that's the beauty of heading to the bench and experimenting. And just to finish up, if it's not obvious, but you might see it in this format down here at the bottom of the screen, where gain bandwidth product is simply the gain times the bandwidth. And then you can do the algebra you need, of course, simply. If you have a gain bandwidth product rating from the data sheet here, and you know what gain you need, then you can solve for the bandwidth that you'll have right here. I'm down here in the bottom corner if you can't see, bottom right corner. So again, if you had the gain bandwidth product rating from the data sheet, maybe you know the bandwidth that you need, and then you can solve for the maximum voltage gain that you would be allowed to set your circuit up for to hit that bandwidth. So this is the relationship here that you use to determine, for a given gain, how much bandwidth do you have, or for a given bandwidth that you need, how much gain can you do, all based off of the manufacturer's gain bandwidth product rating for their op amp. So a really good op amp will have a high slew rate and a high gain bandwidth product, and then it'll have a higher price too. As always, each individual concept is simple, and then if there is any difficulty, it's usually just holding all the little simple concepts together into what makes the whole picture that we have drawn out here. If you go all the way back, simple, right? It was just when it drops to here, and then that, and so on. So, and how to do it, and on and on. So, like always, we our task isn't that I don't think any one concept is hard to understand. The challenge is keeping them organized and how they fit together.